Triple sum. Given 3 arrays, A, B, and C, of different sizes, find the number of distinct triplets, P, Q, and R, where P is an element of A, written as P something A, Q something B, and R something C. Satisfying the criteria, P is less than or equal to Q, and Q is greater and equal to R. Okay. For example, A has 3, 5, 7, B has 3 and 6, and C has 4, 6, 9. Now I will note one thing already. It says you're given 3 arrays of different sizes. So 2 of these have the same size. So that's a little bit contradictory a little bit already, but fine. We find 4 distinct triplets. 3, 6, 4, 3, 6, 6, 5, 6, 4, and 5, 6, 6. Because of that criteria that we set up already. So complete the triplets function. It must return the number of distinct triplets that can be formed from the given arrays. The naive solution would certainly be to loop through everything, right? So you can loop through the center one, the Q, because B has the Q in it, right? So you loop through the middle one, and for each value in B, you loop through the other 2 to see which ones meet the criteria, and you return I think it's a permutation for each one, because the middle one is like for each combination between the left, you have another combination with the right. So you basically multiply those 2 numbers together. So naive solution, loop through B, match cases in A and C, and then return results. Wait, are there distinct numbers? So it must. So that's part of it. So you must return the number of distinct triplets. Oh, I see. Distinct in the sense that the first and the third might have the same numbers. So let me just see this situation here. So like a 1, 2, 2 would be the same as a 2, 2, 1. Is that correct? Look, yeah. Here's a situation that is kind of contradicting. So it's unique within the subset. So 1, 3, 3 is different from 3, 3, 1. Okay, and I will store the matches. So I'm going to const store A equals a new set. Store C, I should say. It's another set, and loop through B. Okay, so for const num of B, we check if. Then we basically loop through A as well. So for const, so num B, I should say, num A of A. If the logic holds that num B is greater than or equal to num A, then we add it to the set. Store A. I think it's add num A. I think we need a store for B too, actually. Now that I think about it. Store B, add num B. I think I'm just going to copy this for the other one. So num C out of C. Num C has the same logic. C add to A. Okay. So this logic is there, and I'm curious what I'm going to return, but I'm going to console log some of this stuff already. Store, basically the stores. Store A, store B, store C, just to see like what it's coming up with. I think it should be very close to the answer anyway. Num A, num C as well. Okay. All right. Undefined store 1, 2. Okay, so this is the answer here is 8. So all of these. And then all of these, so that's what, 6? I kind of want to like write this stuff out too. Let me just write out all the possibilities here, because it's I think it should be fine. So 1, 2, 1, 1, 2, 1, 3, 3, 2, 1. Wait a second, hold on. It's the pair, right? It has to be when both are true. So for the triplets, they all need to be true. Okay, so let me rethink this a little bit. So I don't think I need the stores actually. let's do the case here, and when these things are true. Okay, so this is not efficient at all. I recognize that, but I gotta try. All right. Okay, cool. So you loop through everything in B. You loop through, and then if it matches the criteria, then you can say, okay, let's look through C. And then if everything in C looks good, then we can say, okay, these things are matching up. We can increment by 1. And we don't need this. And then we can return out. I'm curious if that will just work. It did for some. Okay, I got 8 there, 12 there. This one didn't work. Why? So basically, the numbers on the left and right are less than or greater than the numbers on in the middle. 1, 2, 1, yes. 1, 2, 2, yes. 1, 3, 1, yes. 1, 3, 2, correct. 1, 3, 3, correct. 1, 3, 1 comes up again. Is there another one? Oh, they're not unique. It came in with more than one. The middle value doesn't have a... Okay, so the middle one has to have unique... yeah, so the middle one here has 2 3s. That's why. So you need to make sure those are unique. That's all. Just gonna do something quickly. Crap. So yeah. Okay, and then store B is what you're looking for numB in store B, and I think that should still work. Yeah. Okay. Yeah, it's not very efficient. I know I could probably increase the efficiency somehow. 2 minutes, 44 seconds. So some of these are timing out, so that's definitely a good sign, or not a good sign, but a sign that this is working. It's just not efficient. And for sure, you have to remember that all these are very large arrays potentially. I think throwing this into a set is quick and shouldn't be too bad. Let's do some efficiency stuff here. Okay, so I have an array there, and basically I need to say, okay, so if store.b has it already, numB, then we can skip because we don't want to look at it again. Continue. Actually, I don't see a difference between finding the set, doing the set with that. Or I should say add here. So if you have B, then just continue. Otherwise, you add B, and then you will keep going from there. So B exists, then you go through A. Do I have a store for all 3 of these then? I mean, that's a possibility too. I don't think I want to sort this. Definitely not. I do not want to sort these numbers for sure. Or do I? Let's see. So if I sort them, then I can easily loop through the A and C efficiently, effectively. But is it worth it? Is it worth sorting this giant array first? Well, I mean, is it? Maybe it is, because otherwise you're looping through it all the time, right? So let's think about that. So let's assume we're doing a quick sort. We do this quick sort first, so it's out of the way. Then anytime we loop through the array now, we're only looking at the numbers we absolutely need to look at, which is beneficial for sure. Okay, you loop through them individually, back to back, and therefore, and then you keep track of their individual sums effectively. So let a total. Naming. Oh my goodness. Okay. And then you have your C total. At the very end, I think you do a comparison. Is that what I'm thinking? Well, aren't they? So aren't these two things independent? They are, right? So I don't need to wait on A. I could just say the total is A. So if A total is equals to 0, then I can continue there as well. Right? I don't even need to look at it. Yeah, okay, here. So you have the 3, 5, 7. So 3 and 5 go on the left here. So you have 2 of those. You have your center 2, which doesn't matter at this point. It's just 1, okay? And then on the right you have 4 and 6. So you have 2 and 2, therefore you multiply them together to get 4. So it is a multiplication thing, and that is what I'm looking for. Okay, so out plus equals total A total. times C total. And if C total is 0, then you will basically add nothing, because you don't need a check here to continue. And here I'm adding to this. And here I'm adding to A total. I think that is another way of doing it. Is this more efficient? I don't know if it's that much more efficient. You're still looping through A and B and C. But you're doing it in constant-ish time as N, or I should say A and C constant time versus looping through it twice. I don't know. I'm getting tired right now. What do we got here? You have 0, 0, 0. Fantastic. So what happened? Oh, because it's of store B, so I need to go through B. Yep, that makes sense. Okay, so the logic is sound-ish. Let's see how you do on the real thing. Submit some code. So I'm just concerned about timing out right at this point. I don't think this is the most efficient thing, by the way. So, looping through all the numbers is really crappy. So should I sort it beforehand then? So imagine if I sort it beforehand, then I can just loop through the number until I get to one that's too big, and I just stop. Let's try that. I want to try that. Let's sort this thing first, and then loop through it. Okay. A dot sort, B dot sort. I believe sort is in place, so I don't need to do any reassignment. And then this stuff changes. I'm just going to comment it out real quick, and then do a let's comment everything out here. All right. So I'm still short-circuiting B in case it is a repeat. Yeah, I'm not sure what happens when like A has a duplicate, but it's fine. I'm not gonna think about it right now. So for const num A of A, so I should say while actually. Let I of A equals 0. While I of A is less than or equal to num B I A plus plus. And I do the same thing for C. Okay, and at the very end, my out is equal to. So this sort of short. I want to short circuit this thing. So I'm going to say if A of 0 is less than or equal to less than B, num B. I should be greater, right? Greater. So if you're greater than num B, then we're done already. Same thing with C0. That way I can ensure that it is actually doing something. This while loop's actually doing something, because it's possible that you can stop at the first one, and that counts as a valid number. So IA plus 1 times, I'm going to put like parentheses around this thing, times IC plus 1. I think that should do's it. So let's look at that. The sorting definitely takes a while. Okay, fine with me. Let's look at this. Maybe I'm adding too much for 1. So the number that I found is actually the number it is. So I don't need to modify this at all. Right? That is all I needed to do. I needed to get out of my own way, basically, which is fantastic. Okay, so in the case that you get, in the case that 0 is valid, then you increment by 1 anyway, and you're at 1. So that's why it makes sense. Submit some code. Sorting beforehand. Let's see if it works. It does not. Actually, it does, but it doesn't. So it doesn't time out. So that's actually a good thing. So this is working quickly enough. The sorting is actually okay. So sorting through it once, even though it's big, you set it up so that this process is super quick. So there is benefit in sorting a very large array, even though it sucks to do that. You do it one time, and then you're basically done. And you set yourself up for super efficiency later. So now the question is, why are these failing? Sorted list, yep. Loop through it, yep. Interesting. So this is showing my lack of experience with like the math that's going on. Here they have the iteration for each individual list, for in terms of like the matches, as like an exponential. Like it's like it continues growing. Interesting. So I think I was just missing the math on it. We were dealing with small numbers, but effectively, what I should be doing is not having these stay out here. I should put these out here and have them continue growing. Why does that make sense? So when you have one match, anytime you have a match, you have, I don't know. Let me see if this runs, because I'd rather like try it out and put my head around it after that. So it still works on the test stuff, and it doesn't work on the other stuff. So that didn't help at all. It's still giving me wrong answers. Well, it gave me right answers in other places, which suggests that maybe it does work better than I thought. Yeah, this is basically the same code I had. They sorted B as well. You don't need to sort B. Oh, look at this. Yeah, they do check to see if there's a repeat. Yeah, so I thought there was something funky there. They have to. Yeah, you have to remove repeats then. Okay, so you have to remove the repeats from A. See if that kind of thing works here. I mean, this is kind of the situation I was already talking about, so I don't feel like I'm like cheating really. It's just implementing a concern that I already voiced. Just like kind of annoying because they don't talk about it. They don't even show it in their problems. Like, come on, people. Like, when you're making your problems, make it applicable to your test cases too. Especially if you're going to make test cases that are so insanely large that you can't even test them. Anyway, run some code. Give me 1 second. I have a call. Okay, so I had to leave last time, so I did finish it. I just had to finish it offline, but I did want to come back and show my solution, which actually includes something called a binary search, and I kind of do it a slightly different way than you would typically see a binary search. So I'm going to go through my logic and show you how this thing works. Okay, so first I will take into account the fact that these the arrays A and C may have duplicates, so I create a set and then I kind of convert that back into an array. So there is some added complexity for that, but for the most part the biggest time complexity is the fact that you're sorting it, so it kind of doesn't really matter. Going through it once or twice is just O of n, but going through it with the sort is n log n, so that's the most significant component there. So I sort A and C because that is how to do this problem best, in order to compare. And then B, I just create a set because again there could be duplicates there. So that kind of is the same logic from before. And I have my total as a summation variable. Then things get a little bit different here. So I go through my B array, and if because it's sorted, if I find that the very first element of either list A or C is too big, then I know that there's nothing I can contribute from this from either one, so I can just continue and go to the next number because that B is too big for anything to be used. So once I get past that, then I know at least I have one from each array that is valid. Then I set my iterator for A and I that I'm calling AI and CI. And what I do is I kind of do the reverse of what I just mentioned. So here I'm checking the first element, but what happens when the very last element is actually still less than or equal to the number? In that case, that means all of the elements are less than or equal to the number, and therefore I don't need to do any searching. I can just return the length of the array, because that's how it's just a whole thing basically. So I do that for both A up here and also for C, because that's the same logic. And then I do this binary search, and I have a function I define up above this, but effectively binary search will find and return the indices where the number is just large enough to match this criteria that we have set up here, where it's less than or equal to the number. And I'll show you that in a second. But I'm basically doing it for A and C, and CI will become the indices the indice, which is effectively the length also of the numbers that are valid. And then at the very end, I do have the same logic of multiplying those two lengths together and adding that to the total, because that's the same logic from before. And then I return the total. So how does the binary search work? So typically a binary search will, you don't need to really even look at the code really, but the binary search effectively is taking a sorted array and basically starting in the middle to see where this value is that you're looking for. In this case, we have our number from the B array as our target, and by sectioning off half at a time, we can zone in very quickly on where the target is, and that can be done in log n time. So it's actually a fairly quick way of finding your target. However, because we're potentially looking for a number that isn't actually in the array, we're looking for a number that meets a criteria, we have to do a little finagling here. So here's how this logic goes, and I am pulling this from another source called Geeks for Geeks, and it's to find the closest number in an array. So I'm kind of pulling this information. I actually had this already programmed, but it's nice to have it like from someone else as well. It's not just from my head. And I did have to include this logic here, which I was actually missing, so it was helpful looking it up. So here's how it goes. You start with your start. You have 2 pointers. The start index on the right, well, it's right for me. So you're left. So you're left, and you're right. So the start is 0, and the end is basically the very end of the array. And what you're doing is, while the start and end are not past each other, while they're still like in a valid zone, the while loop will continue going, and then you pick a midpoint, which is just you just do the math. You do the start and the end divided by 2, and that is going to be your midpoint. And I floor it just because you can't have an integer, you can't have a decimal or float trying to do a lookup. Then you check, hey, have I found my number? First thing, is the midpoint the actual number we're looking for? If it is, then I can simply return that mid plus 1, because in that case, that means the number I'm finding is the target number, but what we're looking for is actually the number that's a little bit larger than that, and that the index, I should say, of the number that's larger than that, which is the length of the array that we're kind of looking for. So that's why this is a plus 1. Then I check to see, hey, is the number in the middle less than our target or greater than? That will help us section off to see, that'll help us create the next section that we're going to search through. Basically like removing half of the values that we're not going to be looking at. And here's the logic that I didn't include before that I really needed to, which is the idea that after you've found your middle, which is, once you found your left-hand side, which is going to be the array start, if you find that that number is actually greater than your number, then you've actually found the right spot, and that's where you can stop. That is the logic I had to include because it was messing up. And the reason it's messing up is because the logic we're employing is not just finding the number, but finding a number that is actually greater than, just greater than the number that you're looking for. So the end will be the greatest of the two numbers. So you might say, why not put start or end? Because technically at this point, the start and end will be either on each other or I think slightly past, but the end is still going to be the largest of it. I think the end is still going to be the largest. It's in the right spot. So that's how that works. It was very frustrating to get that working, I know, but it does work, I promise, and it took me a while. But one thing that's really cool is that the binary search is very quick and efficient. So if you're getting timed out on this, the solution is because you're doing too much searching. Anyway, that's it for now. I hope that was useful and helpful. I really enjoyed actually learning how to do the binary search. I think that's going to be very useful in the future. So take care, and I'll see you later. Bye.